Welcome to our last equation derivation that I'm going to record a video about. So my first question to you, how have we defined the area of a velocity time graph before? Pause the video and look back at unit 1, find the answer. What do we define as the area of a velocity time graph? Okay, so you've reviewed your notes and you found out that we define the area of a velocity time graph as displacement. Oops, misspelled that. Can't type. Okay. So here in Unit 3, our velocity graphs don't look like horizontal lines as they did in Unit 1, but they look linear. And so how are we going to find the area of a linear graph? Well, just like we did back in Unit 1, we can find the shapes that make up our graph. And so this graph has, I'm going to make it a little bit transparent. So we've got this rectangular shape that fills in this blank space below our initial velocity. And then we also have a triangle that I'm going to have to flip it. Oops, not like that. Flip horizontally. And we've got a triangle. And so we can calculate the area of these two separate shapes, and then the total area is equal to our displacement. And so displacement, which is delta x, we need to get a special character. Displacement is equal to our rectangle plus our triangle. So let's calculate the area of our rectangle. Well, it is V0, V naught high. So area of a rectangle, first of all, is base times height. So V0 times, that's our height, times our base times height, times our base, which would be times t. That's how wide it is. And then for a triangle, it's 1/2 base, which is t, times height. And our height here is v divided by, or v minus v naught. But what we know from previously, that we can substitute something in for v minus v0. And so let's take a look at that maybe over here. V minus v0 is equal to, I don't really want to have that, is equal to our acceleration times our time. And I got that from our old equation. Acceleration is equal to our change in velocity divided by time. And so if I multiply both sides by time, I get the change in velocity is just acceleration times time. So going back here, we can substitute that into our equation and get that our change in position is equal to v0 times t plus 1/2 a times t. Whoa, no, I lost my page. A times t times t. We just substituted that in, and we would get 1/2 AT squared. Oh gosh. And here we have our final equation. And this equation is very similar to what we found from our position versus time squared, where we found back in position versus time squared that it was equal, position was equal to 1/2 AT squared. But we've added now this initial velocity term. So this equation is true even if there is an initial velocity. Before, we had the caveat that it was only true if there was no initial velocity. Okay, so that's one way to find this displacement, but there is another way. So displacement is equal to the area under the velocity time graph, or the area between the velocity time graph and the horizontal axis, the time axis. So we can also look at this shape another way, where it's really it can be the same thing as a square, where we've got this. Let's see, I'm going to make it a dotted line. So we've got this value in between V naught and V, maybe like the average value, where this area up here, let me show you, this area here is equal to this area here. And so instead of calculating a rectangle and a triangle, we could actually just calculate the shape of this rectangle here, which let me color in with a custom fill. Maybe I'll make it red colored. And so we could calculate the shape, the area of this red box, which would also be our displacement. And so let's go ahead and do that quickly. So base times height, so delta x is equal to, well, this value here is the middle value between our initial and final velocity. So we could write that as v plus v0 divided by 2. That's our average value. All I've done is calculate the middle times our base, which would be time. And so this is another one of our big famous equations for this unit, where displacement is equal to the average velocity times the time. And so that is how you get these last two equations in our summary slides. We've got displacement using average velocity, and then our displacement using the area of the rectangle and the triangle. I hope this was helpful. Let me know if you've got any questions. I'll see you in class tomorrow.